right? Because the p to the n plus 1 goes to 0. Okay? How is this derived? I sometimes think it's useful when it's easy to derive things, you may as well see how to derive it. So let f of p be this sum. So 1 plus p squared plus p cubed plus p to the n. Right? And then p times f of p is going to be p plus p squared plus dot 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 plus p to the n plus 1. Right? So p f p, let me write this way. P f of p minus f of p is going to be p to the n plus 1 plus all these terms minus all these, so everything cancels out except for the p to the n plus 1 minus 1. Right? And then you can divide by p minus 1. So this is p minus 1 times f of p. Right? So hence you get that f of p is p to the n plus 1, sorry, plus minus 1 over p minus 1. And what I wrote over here is just, I reversed the, negated the numerator and the denominator. Okay? And in a similar vein, you can prove, and in fact, the TI and his solutions does this, that I equals 0 to infinity of I p to the I. I don't remember it off the top of my head, but it's easy to derive. I think it's 1 over 1 minus p squared. Well, another way to see it is you take the derivative of this, you get this. Derivative with respect to p of this term equals this term, right? And so obviously the derivative of the left-hand side, where are we? Derivative of the left-hand side has to equal the derivative of the right-hand side. Take the derivative of this, you're going to get that with respect to p. Okay, so this equals PdP of the sum of p to the I. Okay, therefore it has to equal ddP of 1 over 1 minus p, which if you remember how to do calculus, 1 over 1 minus p squared.
Wait 3 minutes.
Yeah, I know. It sucks, doesn't it?
I was waiting classic like.
Learn the hard way. All right? I dropped the lowest score anyhow, so you lost your freebie. That's it. But you still learned. You had to learn, right? That's the important part.
I don't know math semester.
Huh? Yeah, well, get here on time. Everybody else seemed to manage it. And you know, there's other ways to turn it in early. So take advantage of those if you can't get here on time. All right. So that sort of concludes discrete probability. So now we're going to move to continuous probability. So any questions on this or on any of the homework?
The problem with the n people in the room were like number 4C.
4C.
We were trying to find
The expected number of pairs of people. Uh-huh.
It was a little tough.
You didn't get the hint?
No.
So we want to count the number of pairs of people with the same birthday. And so if 3 people have the same birthday, that counts for 3 pairs, right? AB, AC, BC. Okay? So you let n equal the number of pairs of people. The same birthday. Okay? If I let xij be an indicator random variable, which is 1 if person I and person j have the same birthday, right, and 0 otherwise, then this is true, right? The number of pairs is just going to be the sum of these xij's, right? Covering all ij where I is less than j. Right? I'm basically iterating and counting all the pairs. So E of n is E of this sum okay, which by the law of expectations is that, right? There are, we say n people, so there are n choose 2 terms in that summation, and each one of these is just 1 over 365. Right, the probability that 2 people have the same birthday. Sorry, so sorry. Probability that xij equals 1. That's 1 over 365, right? And so E of xij, which is going to be 0 times 364 over 365 plus 1 times 1 over 365. Right, by the definition of expectation. It's an indicator random variable. It takes on value 1 or 0. 1 with probability, 1 over 365. Okay? So you just, so you're done. The answer is just n choose 2 over 365. So again, it's sometimes there's a brute force method that's not the easiest. If you set up the problem the right way, if you can see the trick, in this case, the trick was to pose it in terms of indicator random variables, get it in the form of a sum, you could then apply sum of expectations as expectation of sum, or the other way around. Okay, any other questions? Okay, I'll give you amnesty. You can turn it in. Anybody else? One-time amnesty. Don't push me again. Jeez, I've done this 3 times now, so the word's going to get out. You can be late for the first homework. After I do this, I should just make it not count, right? Yeah. On time next time, guys, right? Okay. Last year, the guy, I did the same thing. He sat back down, ripped up his homework into 4 parts. Fortunately for him. So afterwards, I still let him turn it in. You know, the grader had to tape it back together. But it was only, you know, if he had really shredded it, you know, that would have been it. Okay. Any other questions? So I got a couple of email from people. You know, they kind of got the idea, but not completely on some of the questions. So if you're in that boat, you're not alone. But I want people to really sort of understand. We're not asking very hard probability questions here. So, or I should say, there's a simple method to proceed to solving them. There's not a lot of math, computational math involved, right? So it's just a question of seeing things the right way. So if you're sort of selling yourself short by saying, yeah, I think I know how to get the right answer, not really understanding what's going on, you probably rushed into it too quickly. And you should take a little more time and think about why the right answer is the right answer. So I would advise looking at the solutions, seeing if they matched up with your answer, really trying to understand why that's the right answer. For instance, on problem 6, if you didn't get the right answer, that's that conditional probability question. It's easy to get thrown on a question like that. So, you know, check to make sure that if you got the right answer, you know, that you really understand why it's right. Okay? So now we're moving to continuous probability. So you've seen this before. It's probably raindrops on a line or plate instead of coin tosses. Instead of coins, cards, dice. etc. These things have discrete outcomes. Continuous probability has an infinite set of possible outcomes. Okay? So for instance, I drop a coin, a raindrop falls on a line. It falls here. Boom. I measure the location where it fell. This is an interval from 0 to 1. It fell at point 34762159432. Depending on how accurate my, what's it called? Not chronometer. What's the thing that lets you measure really precise values? Let's go with electron microscope, okay? Right? Presumably you could do it with that. What was, the term? Huh? Ruler. A really good ruler. Okay. Okay, so the problem is that if you were to ask, well, what's the likelihood that a raindrop falls in the same place again? Okay, so let x equal the position. Let's do x sub I. X sub I is the position of the ith raindrop. Okay, the probability that xi equals 0.347 is going to be 0. I mean, there's just so many possible outcomes that the outcome that it falls in any particular place is 0. Well, don't worry about it too much yet. So instead of talking about the probability of a raindrop falling somewhere, we're going to talk about the probability that x is less than some value little x. Okay, and this will have positive values. The probability that x equals x is 0. Okay, it just can't be measured. The probability of a raindrop falling in any particular place is 0, but you look at an interval or a range, and it's got some value. Okay, and so the question is, so how do we talk about a raindrop at a particular point? Because you're going to see it's going to be useful. And that's what's known as the density function. Okay? So remember, so keep in mind that the probability that x less than x is a function on function of x. Okay? Of the little x, not the big X. So for instance, I could say that the probability that x is less than x, that could equal x, or it could equal x squared. Okay, for 0 less than or equal to x less than or equal to 1. Okay? So on our unit interval, okay, the probability that a raindrop falls, if we have probability that x equals x, the probability that it falls to the left of any mark I make. So if I make a mark at the position 0.33, the probability that the raindrop falls over here is going to be 0.33, right? The probability it falls over here, 0.67. Okay, and if it's x squared, the probability that falls to the left of here is 0.3 squared, right? And the nice thing about these functions that I chose is that the raindrop definitely falls on this interval between 0 and 1, right? With probability 0, it falls somewhere to the left of the 0, and with probability 1, it falls to the left of the 1, right? So it's all contained within the range 0, 1. So the density function of x equaling x, we can actually define it in terms of equality, is going to be defined, so this definition, as the derivative with respect to x of the probability that x is less than x. Okay? So, if the probability that x less than x equals x, then the density of x equals x is 1. If it's x squared, then density of x equals x equals 2x, right? Just taking derivatives. Yeah, and one aside. For continuous random variables, that we'll be considering because you can always get a lot fancier. You know, mathematicians can really think up some weird phenomena that don't happen in day-to-day life. You know, they happen in quantum physics and relativity and stuff like that. But for the most part, for the stuff we'll be studying, it doesn't happen. For continuous random variables, the probability that x less than x equals the probability, or let's say probability that x less than or equal to x, little x, equals the probability that x is less than x. Okay? Why is that? Anyone? Huh? Because it's continuous, but so what? Yeah. I mean, this you could rewrite as the probability that x less than x plus the probability that x equals x, right? These are disjoint, so this or this is just the sum of them. So we already said that this is 0. So the probability that x less than the probability that x less than or equal to x equals the probability that x is less than x. Okay. And so it shouldn't surprise you that the integral from minus infinity to, let's say, x equals that, right? I mean, you take the derivative one way, you take the integral in the other direction. So I don't know how well everybody grasps intuitively what calculus is telling us. So this is basically telling us when you take the derivative, looking at the rate, right? The rate of change. So it's the rate of change of the probability, right? So you know, as you're moving across this line, we're asking if I move another infinitely small step, a distance delta t, and we're going to crush delta t to infinity, how quick is the probability going to grow that the raindrop falls to the left of I'm sliding some stick. How quickly is the probability growing that it falls to the left of the stick? And the way to think about that is now to look at the integral, right? This is x, and this is density of x. Okay, and you know the density function is going to go something like this. And basically, if you remember calculus, the area under the curve, right, is the value of the integral, right? So all we're asking when we're doing this is we're taking little slices of size delta x, right? And we're asking if I move the stick over another delta x, how does my probability increase? I mean, I'm saying the same thing as I said before. So when you're doing the integral, you're actually summing those together, right? So the derivative is telling you the rate at which it would increase, and when you're taking the integral, you're actually computing the probability by taking these little slivers, where the density, the derivative tells you how much it's going to increase by if you had a sliver, and you know you multiply that by the size of the sliver, and the integral is a nice way to sort of crush the width of the sliver down to 0. It's the limit. So people kind of grasp how integrals work. Who follows me? Just out of curiosity. Who doesn't follow me? All right. Nobody put up their hand. If you put up your hand, I would. Who wants me to try and repeat this one more time? Nobody. Okay. Either I'm getting better as a teacher, or people are just giving up. If there's any hope. But it's important to understand this, because again, if you don't, you're going to get confused later on. Yeah. New eraser, right? Because last time. Oh, just something else to clarify some people's confusion. The TA's office hours that's Richard. Well, Richard is really his alias, but his real name is Tian Bai Ma. It's Monday, 2:30 to 3:30. Thursday, 4:30 to 5:30. Okay, so some people thought those were mine, and it's in 8LE5. Mine are still in. This is Sepser, also in Sepser. I mean, this is on the webpage. I think it's Tuesday after class. No, Tuesday 4 to 5. And then Wednesday after class. Which makes sense because we don't have class on Tuesday. Okay. Back to density functions and continuous probability, etc. So now we can talk about the expected value of a continuous random variable. Okay. That's going to be the integral from minus infinity to infinity of x times the density that x equals x dx. Okay? Looks a lot like the probability formula that you have for discrete random variables, right? Except instead of a summation, you've got an integral. Instead of probability x equals x, you've got density x equals x. Okay? And again, you think about the approximation, right? Where here's your density. So this is x, this axis, and this is density of x over here. Okay? When you take the integral, you're breaking this thing into infinitely skinny slivers. Right? And we're saying when x takes on this value, okay, this is sort of describing how much the probability changes. So this area is sort of what fraction of the time it takes on this value. Then you want to multiply it by value, right? That's how you compute the average. And then it's just squishing these things down. This is approximation, and by squishing or making the infinite number of intervals or squishing the width of the intervals to 0, the approximation becomes more and more accurate. And the integral is the limit of that squishing down. Okay? My dad always used to like to tell me, when I was in high school, he was like, Newton, Newton invented calculus by the time he was 16. You know, what are you doing? And it put a lot of pressure on me, right? No, I was like, you know, leave me alone, Dad. My dad didn't invent calculus by age 16 either. That's what I should have said, right? You didn't do it either. Oh. All right. Newton was clearly a pretty smart guy. What? Oh, yeah. Okay, just like this is equivalent to the definition of how you compute the expected value to the discrete case, this is also similar to the discrete case. Remember this? That E of x equals the sum from I equals 0 to infinity for the probability that x greater than x for a probability x greater than I in this case. For discrete integer valued random variable. Right? And then I have something in my notes here that about how to prove this. Let's see if I actually want to do this. Is that the best way to show it? No, there's a better way to show it. Well, just in case people are curious, how do you see this? How do you see that this is equivalent to that? Okay? And in fact, we're going to use the same trick that we used here. Remember what we did was we sort of reordered the terms of the sum. There was the columns and the rows. We're going to do the same thing here. You'll have to excuse my eraser. All right. Okay, so what's the proof? Well, we're saying the integral from 0 to infinity of x density x equals x dx. Yeah. That's going to equal the integral from 0 to infinity, the integral from 0 to x dy dx. Right? If you do this integral on the inside, I'm integrating the same value from 0 to x. Right? So I'm just going to get x times density x equals x. Right? Everybody see that? The integral on the inside. This is just x density big X equals little x. Okay, now I'm going to reverse the order of the integrals. So I'm going to get the integral from 0 to infinity So, okay, notice the thing about x and y when I'm doing these integrals here, okay? Y is always less than or equal to x, right? Y goes from 0 to whatever value x is. So if I'm going to reverse the order of the integrals, then y is going to go from 0 to infinity, and x has always got to be larger than y. So x goes from y to infinity of the same thing, density x equals x, dx dy. Right? Everybody see that? I mean, again, the only trick is when I'm reversing the order. You have to make sure you run through the same values of x and y. So over here, sorry, this is x and this is y. So y covers all values that are less than x. Or in other words, x covers all values that are larger than y. So when you reverse the order of the integrals, that's what you get. And this, now the integral on the inside, this is just the probability that x is greater than y. Right? Density that x equals x, where x is ranging from y to infinity, is the probability that x is greater than y. Or greater than equal to. The equal part doesn't really matter. Okay? Which is just the integral from 0 to infinity of probability x greater than y dy. Right? Last year I proved it by parts. It's not as elegant. Okay, so any questions just sort of about the theory behind continuous probability? Because we're going to start talking about particular distributions now. No questions? Okay. The less important distribution for this class, but it's more intuitive. Distribution. It's the uniform distribution. Which basically says the intuitive explanation is the outcome is equally likely to happen anywhere. Let's put on a constrained interval. Okay, so if I have an interval, let's say it goes from A to B. Let's use lowercase letters. Okay, so 0 could be somewhere over here, and the interval could just keep going. Well, if it's uniform, if the event that's happening is uniformly distributed on the interval AB, then something's equally likely to fall here as it is over here. Okay, or something's equally likely to fall in this range of length L as it is to fall in this range of length L. Okay? If the rain drop location is uniformly distributed on the interval AB, okay, and again, we don't care if we use brackets or parentheses because we don't care about the endpoints because the probability of something actually happening at an endpoint is 0, right? If the rain location is uniformly distributed on AB, then it is equally likely to fall in any interval of size L within AB as in any other. interval of size L in AB. Okay? So what can we say about, well, somebody tell me something interesting about the uniform distribution. Anything, yeah. Yeah.
So the density function is, there really is no density function, or it's the same throughout?
Well, you're on the right track. Yeah, okay, you said it. That's the point I wanted to make. Is for the uniform distribution, the density function is a constant. Okay? Basically meaning, again, if you think about the intuitive notion of density function, the rate of change of the probability, right? In any stretch of space, no matter how big I choose to make it, basically the probability has to have changed the same amount, right? So the density function has to always be constant. People see that? So, in particular, the density function for a continuous, uniformly distributed random variable on the interval AB is, for a constant uniformly distributed random variable, capital X, on the interval AB is density x equals x is what? Yeah. Close. That would be negative.
1 over b minus 6.
1 over b minus 6. For a less than x less than b. We can do less than or equal to. That's fine. Right? For anything less, for anything, for x less than a, or x greater than b, density of x equals x is 0. The event can't happen up there. Okay? And this way, if we integrate from minus infinity to infinity of density x equals x, well, it's 0 everywhere except between a and b, so that's just going to be from a to b, density x equals x, which is, as we, dx, which is the integral from a to b of 1 over b minus a dx. And if you do the integral, you get 1, right? So again, the probability that we fall inside this interval is 1. Okay? What about the probability x less than x? And x is uniformly distributed RV on AB. What's the probability x less than x? What does it equal for? What does it equal for x less than a? 0. Yeah. What about for x greater than b? 1. And what about inside the middle of the interval? linear. True. Yeah.
X by b minus x upon b minus
X over b minus a. Close, but not quite.
minus a.
Okay, so when x is a, it's 0. When x is b, it's 1. Right? When x is somewhere in the middle, it's, sorry, what was your name? Yeah. Emil. As Emil said, it's linear. Right? It increases linearly.
Okay, how do you see that?
How do you,
A over B minus A.
well, you could have gotten it from the integral from a to x of 1 over e minus a dx, right? But it also comes from just the observation that it's linear. It's got to be 0 at a and it's got to be 1 at b. And this is the only linear function that satisfies that property. Right? I mean, basically, you got something like a straight line between a and b that equals 0 at a. It's got to look like this, right? Probability that x is less than x. Here's a. Here's b. Here's 1. It's got to go like that. That's the only. That's a uniform distribution for probability x less than x on AB. And this is 1. Okay? Okay, why do we hate uniform distribution in this class? You're going to see we love the exponential distribution. But why do we hate the uniform distribution? Because it's a real pain when dealing with history. Also memory or conditional probability. Okay, so suppose I tell you again, x is uniformly distributed on interval AB, and now I can ask you, what's the probability that x is less than some x, given, I'm trying to think of a way to make this interesting enough. Yeah, I guess it's not that interesting. All right, given, let's do it this way. Let's do z less than x is less than y. Okay, what does that look like? Oh wait, this way, wait. Let's say let's make z less than y less than x. Okay? So what is this? And the answer, just start off by using the formula. It's going to equal the probability that x is less than x, and let's just this way. Z is less than x, and x is less than y. Divided by the probability that Z is less than x, x is less than y. Okay? And we have that y is less than x. So if capital X is less than y, then it's also got to be less than x, right? So this is redundant. People see that? If we're trying to figure out probably that x is less than x and less than y, and we know y is smaller, well, if it's less than y, then it's less than x and y, and if it's not less than y, then it's not less than x and y, so we can sort of stop worrying about x. Okay? So, well, if you were to do this out, let's see, what you would get, I think the numerator is kind of a mess. I think it's y minus z or b minus a. Yeah. And the denominator wait. Where z is less than y is less than x. Of course, it's going to come out to be 1, right? If you know that x, capital X, lies in this region between z and y, if you know that and you know that y is less than x, then of course capital X is going to be less than x if you know that it's less than y, right? So, sorry, let's change this around a little bit. Be less than x, less than y, and now this becomes redundant if this is true, right? Now, if just by changing the order here, if we have that x is less than x, then we know it's got to be less than y. Sorry, if capital X is less than little x, then we know that capital X has to be less than little y. Okay? So this becomes x minus z over b minus a divided by y minus z over b minus a, which equals x minus z over y minus z. Which I guess isn't all that complicated a formula and doesn't really make my point for me, but the point I'm trying to make is when you do conditioning, you have to do some computation to figure out the conditioning. Yeah, Sebastian.
If you had chosen the other one, like x is less than y, it would have got like 1.
Yeah.
So, but you can't do that.
You can do that.
You have to include the little x.
Oh, no. I changed this around because I was getting 1.
Okay.
The point of the example was it's not a nice distribution. If you get 1, it's like, hey, that's great. But that would be true for any distribution. I mean, this probability, the way I had it written before, would always be true. It would always equal 1 if y is less than x. So this is not such a great example. But I guess you'll see it's ugly. In contrast, the distribution that we're going to be using a lot of in this class that you don't need intuition to use, but having good intuition with it saves you a lot of time. So I highly recommend you develop intuition. It's the exponential distribution. Which is the probability that x greater than little x. The greater than I want to do? Yeah. Is e to the minus lambda x. Okay? Where lambda is the rate of the random variable. Okay? And x is non-negative. Okay, that's always true for the exponential distribution. X is always non-negative, and then we have this parameter that's going to be called the rate. And not necessarily true for uniform distribution. Uniform distribution, you do have uniform distributions where the value of the random variable can be negative. Okay? We'll get to that. Just for now, just think of it as a parameter. But we'll get to, and why it's called the rate becomes very, very useful in our context as well. Okay? The density of x equals x is going to be, take the derivative, minus lambda. That can't be right. Hang on a second. Huh? I always get. I can never remember if it's 1 minus or just this, but I think. So when little x is 0, you should have 1, and then it should decrease. So that's right. Oh yeah. Duh. Sorry. So I was right up. The density that x equals x is the derivative of the probability that x is less than x. Right, that's where I was confused. Which is d dx of 1 minus e to the minus lambda x. Right? So the density is going to be lambda e to the minus lambda x. Okay? Okay, now I'm gonna show you what it's really the one cool thing about the exponential distribution. But it's so cool, okay? I mean, when you're first starting out in math, you don't really appreciate this. But believe me, come homework time and midterm and final time, when you can just apply this property, it's called the memory property. When you can just apply this property, it's like when you're actually doing research and this thing kicks in, you're like, yeah. That's about as excited as you can get about math, right? I remember professors always used to say, when I was a student, they'd say, "This is a beautiful result," and I was, like, how can math be beautiful? I think you have to go through the process of research and really struggle with things to learn to appreciate the beauty of results. But when you're a student, it's just another equation. It's long, it's short, But, all right. So, okay. So what's so great about the exponential distribution? It's the conditioning. How nicely it works when you do conditional probability. Okay. Let x be an exponentially distributed random variable with rate lambda what is the probability that x is greater than a, right? We already said, by definition, it's e to the minus lambda a. Right? Oh, and yeah, and again, the point is when a is 0, this is 1, and as a grows, this goes to 0. Right? Okay? So here's what's so neat. What is the probability that x is greater than b given x is greater than a, okay, where b is greater than a? Okay. So again, you just plug in, right? If you just compute a conditional probability, it's the probability that x is greater than b and x is greater than a, divided by the probability that x is greater than a, right? Since we know that b is greater than a, x greater than b and x greater than a is just x greater than b, right? If it's greater than b, it's got to be greater than a. So x is bigger than b and x is bigger than a. All you got to say is x is bigger than b. It's the same probability. People understand that? Follow that? Why x greater than b and x greater than a equals probability x greater than b? Let me show you. Here's all possible values of x. Okay? Here's the set where x is greater than a. Right? Now I'm going to draw the set where x is greater than b. But since b is greater than a, if x is greater than b, then it's got to be greater than a. Right? So x greater than b falls inside x greater than a. So when I tell you x is greater than b and x is greater than a, all you really need to know is that x is greater than b. If you know x is greater than b, you already know it's greater than a. Right? So the probability that x is greater than b and x is greater than a equals the probability that x is greater than b.
What happened to the
Denominator. Oh, I just haven't finished.
Oh, okay.
I was just explaining the numerator. But okay. Now, okay. Which is what? Which is e to the minus lambda b divided by e to the minus lambda a, which is e to the minus lambda of b minus a. Okay? So what's so fantastic about that? Well, here's why we call it the memoryless process. And there's a lot of ways to think about this, so let me try and explain. Let's see. Yeah, okay. Let me put it this way. This is the way to think about the memoryless process. Okay? And it sort of counters your intuition. So suppose Professor Rubinstein's wife takes a phone call at time t equals 0. And the time until she hangs up is exponentially distributed with rate lambda. Okay? So let's call this time. Let's call that x. Okay? So what's the probability that she talks for more than an hour? It's just going to be e to the minus lambda times t equaling 1 in this case, right? So it's just e to the minus lambda. Okay? What's the probability she talks for longer than 2 hours? Well, let's do 3 hours. Let's do 3.7 hours, just to do something kind of weird. E to the minus 3.7 lambda. Right? Now suppose Professor Rubinstein's waiting for his dinner because he cooked it for him and his wife, and he's a chivalrous guy, wants to eat dinner with his wife, but she won't eat. She's talking on the phone. So let's say I go in and I check to see if she's still on the phone. All right. So what's the probability that she's still on the phone after 4.7 hours? I mean, again, it's just e to the minus 4.7 lambda. Nothing interesting so far. Okay? Suppose she's been on the phone for an hour, and I check, and I see that she's on the phone. Okay? So I know she's going to be on the, if I check after an hour and she's on the phone, I know she's going to be on the phone for more than an hour. Right? So what's the probability that x is going to be greater than 4.7 given that I checked on her at time 1? Okay? So this is sort of asking, what's the probability that she's on the phone another 3.7 hours given I checked after an hour? Okay? If you do the math, it's going to be e to the minus 3.7 lambda. Okay? It's as if she just picked up, it's as soon as I check and I see she's still on the phone, it's as if she just picked up the phone. The probability is on for another 3.7 hours is the same as like when she first picked up the phone. Right? The probability she's on the phone for 3.7 hours there. So every time you check on the experiment, it's like it resets. Kind of counterintuitive, right? I mean, if I didn't check on her, probability she'd be off phone after 4.7 hours is e to the minus 4.7 lambda, which is smaller than e to the minus 3.7 lambda. Okay, there's a certain likelihood she's going to get off at this point in time. If I check on her after an hour, it's like the whole thing resets. It's like, well, you checked on me, so now I'm just going to continue talking. Okay, and the way to sort of think, the way to sort of get the intuition is to think of light-tailed distributions and heavy-tailed distributions. And to know that the exponential random variable is right in the middle, or the exponential distribution is in the middle. So we're more, in real life, we're usually more familiar with these. Okay? Light-tailed distributions. If you check on something, then the likelihood that it's going to end in a certain period of time, the event becomes more likely as you continue to check. So you're waiting for the subway train, right? You look, it's not here. All right, but you check. But it's more likely to come in a shorter time span because it didn't come for a certain period of time. Right? That's what I mean by checking. Like you checked, it hasn't come in the past, so it becomes more and more likely to come. Like waiting for the train. Okay? heavy-tailed distribution. I hate to get political in class, but it's like the war in Iraq, right? When the war in Iraq started, you know, it could have lasted a month, mission accomplished would have been over, right? Now, I mean, what do you think? After it's dragged on for this long, what's the likelihood it's going to end in another month? Not very likely, right? The fact that you've known that it's been going on for a while, it only increases the likelihood that it's going to take a certain additional amount of time, right? Or it could end on November 3rd or 4th, right? Given that that's election day, right? But you know, barring that, right? As these things tend to go on in time, the amount of time you expect, you know, you checked on it. All right, if I didn't know about the past history of the war in Iraq, and you asked me what's the likelihood it would go on for another 2 months, I would say that's, you know, more than 2 months. I would say that's not very likely. But if I know the war has dragged on for years and years and years, the likelihood that it's going to go on for years and years and years increases, right? So that's a heavy-tailed distribution, like the war in Iraq. All right. So you get what I'm saying? Like heavy-tailed. And so exponential distribution really is, past history tells you absolutely nothing. You know, it's like if a train was exponentially distributed, if the time you were waiting for the train, then the fact that you've been waiting a half an hour doesn't make it any more likely that the next train is going to come. Right? I mean, I guess in some sense the subway's not a great example. If people have been waiting for a long time, you may expect it's going to take a long time for a train. Let's say you knew the train ran regularly. Okay, think of a train that runs on schedule. Then the longer you wait, the more likely the train is going to come in the next 10 minutes. Okay, for exponential distribution, you basically learn nothing. Okay, I think what it confuses people's intuition is because they're used to events that definitely happen at a certain period of time, and the exponential distribution is a probability that this thing can happen no matter how big you make it. Your number could happen after that point in time. Okay. So here, okay. So for those of you who took probability with Kaufman, I told them here's a great way to explain the exponential distribution and the memory property. And boy, did he yell at me because he said it's a horrible example, you know, because it's wrong. It can't possibly happen. But that's my whole point. I mean. The concept is somewhat counterintuitive, so I'm going to give you a really weird example that sort of messes with your intuition, and I think it helps. So we got these, and we're going to start looking at these kinds of problems, but in a networking context. But before we get into a networking context, we got two brothers. Okay, identical in every way, except one of them is blind. The other one can see. Okay, and they like to play this game. So maybe the one who can see likes to play the game. All right, the game is they have this dock at their house. They're also very wealthy, so they live on the water. Okay, they've got this dock, and the game is to run to the end of the dock and jump, and see who can jump further. Okay, now both brothers can jump a distance that's exponentially distributed. Okay, well, the one who can see thinks he's got the advantage. Okay, because he can see where the dock ends, so he's going to run to the end, you know, and here, and then he's going to take a jump. Right? And this distance we're going to call x, and it's exponentially distributed. Okay? Well, the one who's blind has a disadvantage because he can't see. So what he has to do is he's got to run and, you know, keep jumping every so often. Okay? And let's assume that he jumps so often that he definitely clears the he doesn't trip and fall in the water. He actually makes a jump, but his jump, right, isn't going to start right at the edge. It's going to start somewhere else. Right? So he's got this disadvantage, right? So who do you expect to jump farther? What's the probability the brother who can see jumps farther? I told you that they jump an exponentially distributed distance. So what do you think? Who's more likely to jump farther? But what does your intuition tell you? The one who can see, right? I mean, he's got the advantage. He goes to the edge of the board, right? But that's where your intuition's messing with you, because it's exponentially distributed. Neither brother has the advantage. Yeah.
I'm sorry. I'm not
What you mean in the physical sense when you say that the guy who can see X is exponentially distributed? What is that?
No, I'm just saying. This is what Professor Kaufman doesn't like about the puzzle, because people don't jump exponentially distributed distances. But let's just assume they do. Okay. Then these two brothers, they play this game. I mean, one can always jump right from the edge because he can see where the edge is, and the other one can't see. So he's just got to sort of jump at random points in time, and let's say we know he's going to clear the deck, but he's not going to jump right at the edge, right? He's going to jump further back, and he's going to be in the air. Okay, so the intuition is that your intuition should tell you that they got the same distribution, the distance that they jump, right? And one of them can see he's going to jump from the edge of the board. Obviously, he's more likely to go farther. But because it's exponentially distributed, that's not the case. Because it's exponentially distributed, they're both equally likely to win the jump. Okay, and so here's how you go about solving this problem. Okay. Let's look at the point where this guy starts his jump. Okay, let's call that 0. That's our distance 0, where the blind guy started his jump. Okay, and let's say he jumped a distance, let's call it little L, before the edge of the dock. Right? Okay, and the total distance that he jumps, let's call that y. Okay? And this guy's distance, we'll call that x. Okay? Yeah. So what's the probability that x is greater than a? That's just going to be e to the minus lambda a, given that their jumps are exponentially distributed with rate lambda, right? Well, what's the probability that this other brother's distance, I mean, in order to beat this brother, right, his jump has to go a distance a plus l, right? I mean, he jumped starting from a distance l behind. So if he wants to go the same distance as his brother who can see, he's got to go a distance a plus l, right? So what's the probability that his distance is greater than a plus l, given that he jumped a distance greater than l, right? Because he cleared the dock. If he didn't clear the dock, if he landed on the dock again, he'd take another jump, right? That's what we said. Okay? So what's his distance? Well, it's going to be e to the minus lambda a plus l over e to the minus lambda l, which is e to the minus lambda a. It's the exact same distribution. So whatever value you pick for a, they're both equally likely to pass distance a. Distribution. Now, unfortunately, in real life, we don't jump distances that are exponentially distributed, right? I mean, if you we're more likely to jump a distance that's relatively constant. So in real life, the blind brother would probably lose. because he'd start further behind. If they always jump 10 feet, right, the blind one's going to, have this disadvantage. But if their jumps were exponentially distributed, the seeing brother has no advantage. So I don't know if that helps with your intuition or messes it up even more. But we're going to be dealing with this kind of phenomenon a lot. We're going to be using collision resolution protocols. Okay, where two devices try to transmit on a line, and they collide, and so they have to back off. And sometimes one has already been backing off for a while, and a new device comes in and starts to back off. And if the back off timers they use are exponentially distributed with the same rate, who's more likely to transmit next? Either one. Don't worry about what I just said. I'm just sort of trying to relay how it relates that. We'll get back into that in more detail. Yeah, Ron.
Maybe the terms light tail and heavy tail?
Yeah, sure. Light-tailed, when you plot the distribution, it drops off quickly. It goes like that. This would be light-tailed, and heavy-tailed. Heavy-tailed looks more like this. It's got a heavier tail. The tail. Okay? So, see you next time. The homework never made it, did it? Oh, it did? Oh, okay, great. So the homework's available. Boy, Yan is quiet. I want to know. The assistant who brought the homework just did it very discreetly. Yeah.